Hello, my name is Tony Fracasso, and I'm a forecaster with the Weather Prediction Center in College Park, Maryland. This presentation will familiarize you with our probabilistic winter precipitation forecasts, or PWPF. I'd like to thank our lead developer and creator of the PWPF, Keith Brill, as well as Mark Klein, our Science and Operations Officer who developed our user-friendly PWPF webpage, and many others at WPC for their help in creating this presentation. First, we'll go over how to access our winter weather products, including the PWPF, before stepping through the nuts and bolts of just how these graphics are produced. We'll try to avoid too much jargon and technical terms, but some basic understanding of statistics will be a big help. Finally, we'll touch on how best to view the PWPF regarding verification. Here's a look at the main WPC page. You can access our winter weather products from either the left menu, by clicking on Winter Weather, or by clicking on the Winter Weather image in the lower right set of boxes. This will bring you to the main page for our winter weather products. At the top, you'll find links to the probabilities of snow and ice, in addition to some other products like the surface load tracks, impact graphics, verification, and a forecast discussion. The images farther down will bring you to either our legacy probability graphics for days 1 through 3, or to our more user-friendly display with many more options. Quick links underneath these images will bring up the indicated snow or ice accumulation thresholds. When you call up the PWPF, you'll be faced with several user-defined options. From left to right, you can select either snow or freezing rain, view by probability thresholds or accumulation percentile, choose the forecast duration time, plot either a zoomable map or a static GIF image, and finally either choose your exceedance thresholds for all forecast hours, or view all exceedance thresholds for the same valid time. You can easily use your mouse and scroll over the time periods or thresholds of interest along the bottom of the blue banner. This example shows the 24-hour probability of snowfall accumulation equal to or greater than 1 inch, ending at 12Z, or 7 a.m. Eastern Standard Time, on November 7, 2014. The zoomable map is a great way to see more detail in your area of interest, but keep in mind that the resolution of the graphics in this display are 20 kilometers, or about 12.5 miles. This will tend to smooth out the graphics, especially over mountainous terrain. Higher resolution data can be found on our FTP server to use in your own display. The other option in the same interface is to view forecast snowfall or ice amounts by percentile. That is, what is the probability that the forecast amount shown in the image will be no more than your chosen percentile? The example shown here depicts the 95th percentile of the 24-hour snowfall accumulation forecast ending at 12Z on November 7th, just like the previous example. This means that there is a 95% chance that the observed snowfall will be less than this amount. Conversely, there is a 5% chance that the observed snowfall will be greater than this amount. Users may select the appropriate percentile value to fit their needs, as well as a couple other overlay options. Generally, the 5th or 10th percentile forms the lower range of a forecast, while the 90th or 95th percentile forms the upper range. This can be helpful to assess the uncertainty of a forecast and to reasonably communicate a best or worst case scenario. The greater the range, the more uncertain the forecast. Next, we'll go through just how these forecast amounts and probabilities are created. The probabilistic information is derived from a combination of the WPC deterministic forecast in addition to 63 other ensemble forecasts from various sources. For instance, suppose this bumpy curve represents a set of snowfall forecasts from the 63 ensemble members at a particular point. Some show relatively lower amounts, and others are higher. The probability of each amount increases upward in the graph along the y-axis. Next, say that the WPC forecast for this point is on the higher end, noted by the red star. This forecast is used for inter-office coordination and does not go out publicly. However, it is used to morph the ensemble distribution such that the WPC forecast becomes the mode of this curve, which is the most likely amount. Seen here is the adjusted forecast distribution that puts much more weight on the WPC forecast, but allows for probabilities of other lower or higher amounts. For this case, the curve is skewed to the left, which means that although the most likely outcome lies at the red star, it is still reasonable to expect much less snowfall. This would represent the 5th percentile as near the lowest amount expected. On the flip side, there is still a possibility of higher snowfall at this point. This is represented by the 95th percentile, which would lie close to the edge of the right side of the curve. The benefit to this method is that it puts the most weight on the human forecast, but also allows the ensemble forecast to morph around it, which accounts for the inherent uncertainty with any forecast. The bigger the range between the 5th and 95th percentiles, the larger the uncertainty is in the forecast. From this distribution, you can easily compute statistics over an area, and that is what is displayed on our web pages. Next, we'll address the relationship between the 50th percentile snowfall forecast amount and the WPC deterministic forecast. Do they have to match? In the lower right is an example of the internal deterministic snowfall forecast issued by WPC that's used for coordination among the local National Weather Service offices. Notice the area along the Minnesota-Wisconsin border, circled in red, where the maximum value is in the second blue shading, or around 9 inches. On the left is an image of the 50th percentile snowfall accumulation that matches the same forecast time from the lower right image. The difference between the two is that the left image incorporates the ensembles with the WPC deterministic forecast, whereas the right image is the human-only forecast. Notice how the maximum value in the red circle on the left is just over 6 inches. You'll notice that other areas do not necessarily show the same amount at the same location between both images, which is perfectly fine. This shows that the 50th percentile does not have to equal the WPC deterministic forecast, because it is allowed to lie nearly anywhere within that morphed curve that we saw in the earlier slides. In this example, the deterministic forecast is higher than the 50th percentile along the Minnesota and Wisconsin border. If you remember from the previous slides, the curve at that point might look something like this, where the distribution is skewed. As a result, the 50th percentile would be to the left of the WPC forecasts, which is the mode or most likely outcome. The second question is, how do you verify probabilistic forecasts like the PWPF? Say you have a single forecast where there is a 25% chance of receiving greater than 1 inch of snow at a given location, and then there is 1.5 inches observed. Was this a good forecast? Well, the answer is not very clear. Evaluating the skill of probabilistic forecasts differs from categorical or deterministic forecasts. If you predict 1 inch of snow will fall tomorrow, but then 3 inches falls, you can assess the error of that forecast pretty easily. But in this case, the forecast is a probability, so you need multiple forecasts in order to verify them collectively. So the short answer for our original question is that we don't really know because it's only one case. The answer through statistics isn't always available right away. Here's another example. Say you had 4 forecasts that all showed a 25% chance of receiving greater than 1 inch of snow. More than 1 inch of snow was observed for the first forecast, but not for the last 3. Again, we ask the question, were these good forecasts? The answer here can be derived statistically, though a much larger sample size would be ideal. In fact, yes, these represent a set of very reliable forecasts taken as a group. Out of the 4 forecasts made, there was a 1 out of 4 chance of receiving greater than 1 inch of snow, and this occurred 1 out of the 4 times. A robust set of probabilistic forecasts, like the PWPF, should be evaluated over several months at various thresholds to determine if it is reliable. That is, are the forecast probabilities accurate over time? Other measures of skill can be performed through different verification metrics. So what have we learned? Hopefully you have enough information to wade through the probabilistic winter weather forecasts produced by WPC. It's not just an automated product, but rather a combination of the human forecaster with ensemble information. The 50th percentile does not necessarily have to align with the deterministic WPC forecast by nature of our methodology. This allows our deterministic forecast, the mode, to have a significant influence on the final probabilities. And finally, verification of probabilistic forecasts requires many forecast and observation pairs in order to assess the reliability and skill of the system. One case should not be used to say whether or not the probabilities were too high or too low, or even just right. This concludes our presentation on the PWPF. Again, many thanks to Keith Brill and others at WPC for making this presentation possible. For more information, please visit our website and consult the link to information about these products located at the bottom of the PWPF web pages.